Hi guys, and welcome to the start of Chapter 8. Today we're going to talk about the center of mass. Now, we haven't really talked about this yet, although we've kind of been taking it into consideration so far with all of our physics calculations, but today we're actually going to look at how do you find the center of mass of a system, and we'll get to the momentum part of it later. So today, what I want you guys to look at is this hammer. It's supposed to be a hammer thrown up into the air, and you can tell that as it flies through the air, it's kind of spinning here. And so its motion is actually pretty complicated, but if you just pay attention to the motion of its center of mass, the center of mass makes this really nice parabola. So that's kind of what we've been focused on so far, really. Whenever we calculate forces and acceleration and stuff, we're calculating that force and acceleration on the center of mass. But the picture itself, if you were just to look at the motion of the hammer and describe it, it would be pretty complicated to do. But describing it with the center of mass is much easier. So, it sometimes helps whenever we calculate the center of mass of an object to think of that object as particles instead of one big object. And you'll kind of see what that means here in a second. So, let's say we have a system that has two particles in it. It has M1 and M2. And these two are sitting on the x-axis. So let's say M1, this first mass, is at x1, and M2 is at x2. To find the center of mass of this two-particle system, this is our equation that we're looking at. We're looking at the total mass of the system. And xcm doesn't stand for x centimeters. It stands for x, the position of the center of mass. That equals the mass of the first object times its location plus the mass of the second object times its location. Now this makes it really easy to do if we have the freedom to move these points wherever we'd like, because we can just set this x1 to be at the origin, and then that makes the math even easier. So if particles have the same mass, it's pretty easy to tell right now that if particles have the same mass, the center of mass would be located right exactly between them. And if the particles have different masses, the center of mass is located closer to the bigger one. Okay, so using that formula that I just showed you, I have a practice problem for you. This one's pretty straightforward. We have a 59 kilogram woman and a 71 kilogram man sit on a seesaw that's 3.5 meters long. Where is their center of mass located? I'd like for you guys to pause the video real quick and just try to do this one independently, because I will show you the answer in about 1 second. All right, you should have gotten 1.94 meters for their center of mass. That is obviously going to be a little bit closer to the guy because he's a little bit heavier. All right, so this one's a little bit more complicated because now the objects are going to be moving, but it's still not so bad. So we have a fisherman in a boat, and he catches a great white shark and becomes limp when it's 300 meters from the boat. The fisherman pulls the shark by the boat attached to the harpoon, and during this operation, the boat, which is initially at rest, moves 45 meters toward the shark. The mass of the boat is 5,400 kilograms. What is the mass of the shark? So we're going to pretend that the water is frictionless in this example because it makes things super easy if we do that. All right, so I'm going to go to my whiteboard real quick for this because I have a little bit more room. So this is the deal. We have our boat here and water, and then we have shark over here. It's a crazy looking fin. Now the deal is, right, if we look at this whole thing as one system, we have the mass and the shark, and those two things together are going to make up our system. So this is our equation. M1, M2 times the center of mass equals M1x1 plus M2x2. Now, this guy is going to be moving 45 meters as the shark gets pulled to the boat. Now, when they meet somewhere in the middle here, 45 meters from where the boat started, they will meet at the center of mass, right? When they meet there, in that moment, their center of mass will be at that location. So this problem's kind of easy because we don't have any external forces acting on the boat or the shark because there's no friction. If there was friction, then things would be a little bit more complicated, but we're not going to journey down that road just yet, or possibly ever. So for this case, it's going to make things super easy if I set my center of mass as my 0 location. So essentially what I have then is that I have a boat that started 45 meters behind the center of mass, and I have a shark that started 255 meters in front of the center of mass. What we end up having is 0 equals m1x1 plus m2x2. And we can say the mass of the boat, 5,400, times negative 45, plus whatever the mass of our shark is, times 255. Now we'd have to do 5,400 times 45. We get 24300. Ooh, 3 zeros. 255 and 2. And then we just divide that by 255, and we get the mass of our shark to be about 953 kilograms. All right, let's go to the next example. So this works all well and good if you have two particles and they're traveling in the same direction or it's along the x-axis, but this method also works whenever you have a three-dimensional object or whenever you have a two-dimensional object, anytime you have something that's going in more than one direction. So we say the center of mass in the x direction is equal to all of those components summed together. Center of mass in the y direction equals my. All of those individual pieces summed together, and same thing with the z component. So to kind of illustrate this, I'm going to do an example from y'all's textbook because it just does a really good job of showing you what this is, and you're going to have a practice problem in your homework set, or in your book set that's similar to this, so I wanted to make sure that you guys saw this one. Now my pen has decided not to work. All right. There it goes. This is 0.4 meters, and this is 0.6 meters, and this is 0.2 meters. And this is 0.2. Okay, so let me just erase that little squiggly real fast because my pen decided to be crazy. So this is a uniform piece of plywood, essentially, is what your book says it is. But it's got this irregular shape. So if we kind of look at this as it being two regularly shaped objects, we'll call them 1 and 2, it makes our work a little bit easier. So in the x direction, we have mx center of mass equals r m1 x1 center of mass, and then m2 x2 center of mass here. And then in the y direction, because we don't have a three-dimensional object, we have a two-dimensional object, right? So we have this m1 y center of mass plus m2 y center of mass. Okay, so the problem with this kind of, I guess, one thing is that we don't have any masses for our piece of plywood. All we have are these dimensions. Now, mass is going to be proportional to area if the object is uniform, right? So the mass is spread out uniformly throughout the shape, so we can use a proportion for area instead of our mass to do this problem. So the area for this big bottom piece, piece 1, has an area of 0.32 meters squared. And then piece 2 has an area of 0.04 meters squared. Okay, so if we wanted to think about, let me erase this real quick. So our center of mass in the x direction, then, if I divide it by the total mass, which instead of using mass, remember I'm going to use area, I have x center of mass equals m1 over the, so I guess I could say A, area of 1 over the total area times that location plus area of 2 over total area times that location of the center of mass. Now the center of mass is going to be pretty easy to find for the individual pieces from our picture because the thing is uniform. We know that it's going to be right in the center. So let's do it in the x direction and then we can do it real quick in the y. So for your x direction, we end up having xcm equals the area of 1, which is 0.3, over the total area, which, oh, that's 0.32. I don't know how that got messed up there. 0.32 over the total area, which is 0.36, times xcm, which is the center of mass in the x direction for the first part, which this guy is going to be 0.4 because we have 0.6 on the top plus 0.2. That means the whole length in the x direction is 0.8. So that means the center of mass in the x direction for the first block is 0.4. Plus, and then we're going to do this guy over 0.36 times the center of mass in the x direction here, which is 0.7 from our diagram, because this is 0.6, and then we go over one more, and there's our center of mass here and here. Okay, so when we solve that, we get that x, the center of mass in the x direction is 0.43. Now you guys can try to do it in the y direction following the same methodology, but you're going to use the y center of mass here. So for this big piece, it would be 0.2. And you should get that the y center of mass is 0.23 meters. All right, let's get to the fun part, which is using integration to find center of mass. It is possible to do this. I'm going to show you guys how to do this using a thin rod. It's the best way to kind of introduce you to this idea. And to be honest with you, I've never seen the AP test ask you about anything different. So we're just going to stick to the basics as long as we can. So whenever you have a thin rod, the first step whenever you're trying to integrate to find its center of mass is to choose a coordinate system. And one way to do this is just to put one end of the rod at the x-axis. So, here's your origin, and then you can just place your rod on top of it. It's supposed to be straight, sorry. And when you do it this way, your mass goes along the x-axis, so it just makes the notation and the calculus a little bit easier, I think. All right, so let's get to what this means. All right, so the center of mass, right? This is our expression even from the last equation, that the total mass times the center of mass is going to equal to the integral of the location along the beam times, integrated with respect to dm, or the mass. So depending on how long it is, depends on how far, or our limits of integration. So if it has length L, we're going to integrate from 0 to L along that length. Now, the problem with this, or I guess the way that this is written right now, is that we're going to integrate x with respect to the mass. So in order for this to kind of make a little bit of sense mathematically and to make our lives be a little bit easier, it's beneficial to think of the mass per unit length as being lambda. Now, this is a unit we haven't talked about before, but it does exist. It's kind of like density in a way, but instead of it being mass per volume, we're talking about mass per length. So it's very similar to density, but this is called the mass per unit length. And the denotation is a lambda symbol. So if we take this idea that mass per unit length is equal to lambda, then we have that lambda dx, or the mass per unit length times the length that we're looking at, will give us the mass for that particular chunk of the rod that we care about. So we're just going to do a little equation substitution, and I'm going to put this into my integral for dm. Now, why did I do that? Well, now I have an expression for my length that deals with x, and it's also allowing me to integrate with respect to x. So it makes our math just make a little bit more sense if we do this little equation substitution. So I'm going to, the lambda, the mass per unit length is a constant. So when I do my integration, that lambda will come out of the integration. So now I'm just integrating x dx, which is pretty easy to do. And I'm going to integrate that from 0 to L. So my integration becomes lambda x squared over 2. And I'm going to evaluate that, from 0 to L. Which means, if I'm going to kind of squiggle this over here to the side, you guys can kind of see where it's already heading up here. But lambda L squared over 2, gives me total mass times center of mass. So then I divide both sides by the total mass to find my center of mass here. So let's take this just one step further that's not in this PowerPoint. And let's say, okay, I have this expression here. But what if I didn't know the total mass of my object? So instead, I can put in L2 lambda over 2. Now remember that mass is equal to lambda times dx. Or in this case, since we integrated from 0 to L, it's equal to lambda times L. Because remember, this capital M represents the entire mass of the object. So if I'm going to use this capital M, I have to use this capital L to show the entire length of the object. So then we can cancel some crud out, and we get L over 2. Imagine that. The center of mass is exactly in the center of the object. Wow! Now, I know this is kind of like a no-brainer, and we kind of took a really long, convoluted road to get to this equation, this answer that you guys probably already hypothesized to be. But we're going to do a quick example of what happens when that's not the case, when it's not so cut and dry, and when the object is not completely uniform in its mass per unit length. So that would be like this example here. A baseball bat that has a mass per unit length of lambda equals AX. So now, instead of looking at the center of mass as a constant, we're going to look at it as a function. So let's go back. Integrating 0L. So this is our original expression that we started with on the last slide. But instead of lambda, instead we have this function of x. Integrate 0 to L for x, ax dx. So this is like saying ax squared. So we're just going to integrate ax squared, and we get ax cubed over 3. And then we're going to evaluate that from 0 to L, and we get al cubed over 3 times m equals our center of mass. Now, again, same thing, right? We have, let me erase this here. I'm going to erase this if you guys don't mind, so I can talk about this next little bit. Now, before, remember we said that the mass is equal to lambda times the length, which is all fine and good if your lambda is constant, but as we can see here, it is not, so we need to integrate because it's changing. So now L represents the total length, right? Because the lambda is changing, it's not a constant value, right? It's dependent on how far along the object that you are. So we need to integrate this. So lambda is ax. So that means that our total mass is actually equal to ax squared over 2. So if I plug this bad boy into this right here, which I'm going to do up here, al cubed over 3 times, now I'm sorry, this should be from 0 to L, al squared divided by 2. We end up with, these guys cancel out, ding, ding, these guys cancel out. We end up with 2/3 L as our center of mass, which is not so intuitive as it was on the last one because a baseball bat is not consistent with its mass per unit length. It has more mass located at the end of its length than it does at the beginning. So it makes sense that the center of mass should be closer to the end than it would be to the handle of the baseball bat. All right, and those are all your notes for today, guys. I will see you all tomorrow.